Hi everyone. So this example problem will help us find or make the connection between work, force, and energy. We define work as a force across a distance, right? So Ft cosine theta. And then we also said that work was the change in energy. So now we'll get the chance to kind of use both to see how we can get this problem solved. And this one matches questions 2 through 5 on your review. I just have them all here as A, B, C, and D. Okay, and let's get right to it. It says, suppose the ski patrol lowers a rescue sled and victim, having a total mass of 90 kilograms down a 60-degree slope at a constant speed, as shown in the figure below. So let me scroll down. There you go. This is the figure. The coefficient of friction between the sled and the snow is 0.1. A. How much work is done by friction as the sled moves 30 meters along the hill? B. How much work is done by the rope on the sled in this distance? C. What is the work done by the gravitational force on the sled? And D. What is the total work done? So 4 questions. And of course, we're going to start with question A. But first, let's highlight everything we believe to be important, right? So the fact that they're lowering, so this is important. They lower this rescue victim per person, right? We don't want them to die. And then we have a total mass of 90 kilograms. That is the sled plus the victim. And then we have a 60-degree slope. And this is very, very important, guys. At a constant speed. Very important. Okay? Then we have the coefficient of friction. And let's start with question 1. Let's use green for that one. How much work is done by friction? And then in this case, the sled moves 30 meters along the hill. Okay, so there it is. And let's start with our given, right? And the given is most of the time is what we highlight or what we underline in case you only have a pencil. And then we look at the figure if we are given one and see if we can, find anything there. So given. Oh, we said green. That was my mistake. Given. We have a mass of 90 kilograms. And then we are told that we have a 60-degree slope. Okay, so normally we would label this as theta, but we're not going to do that yet. You'll see why, okay? Then we have a coefficient of friction. That is the Greek letter mu, 0.1. This is a coefficient. It has no units, okay? And then we have to find the work done along 30 meters. So that would be distance of 30 meters. And we have to find, other video's done. We have to find the work done by friction, okay? Now, we have to know which equation for work we're going to use. And the fact that we have friction, now friction, we learned friction when we were learning about forces. So we have to find the force of friction across a distance, which means the equation should be force times distance times the cosine of theta. And eventually we're going to have to find the equation for force of friction. Okay? And hopefully you can look back into your notes for unit number 2, and that was coefficient of friction. Now, normally we would have kinetic or static. In this case, they're just giving the friction like that, so we'll just leave it no K, no S, times the normal force, okay? Hopefully you'll see the trend, right? You have normal force, force of friction, gravitational force. So we're probably going to have to use forces. Not probably, we're going to have to use forces, right? I'm not trying to hide anything. Okay. And the equation we have to use, we said it was the one with force and distance, would be the work done by friction can be found by this equation. Lowercase f, that is force of friction, times distance, times the cosine of theta. Okay? Again, theta is not 60 degrees. You'll see why right now. For now, we're going to leave this as is. Okay. Now, if we need to find the force of friction, then we have to use forces. If we use forces, we have to draw a free body diagram. Your favorite. So now, a free body diagram based on the person, the victim, right? So I'm going to copy this hill, right? It's a hill. There you go. That way my free body diagram can be very exact. I'm pretty sure you can see what I'm going after. We always want to find that right triangle. There you go. So now I'm going to take that right triangle, and then of course I use this as a guide for the forces because we have a few. 3 forces listed right there. Oh, come on. So then I move it. There you go. That looks okay. Now we're drawing the free body diagram so we can find the force of friction. Because for the force of friction, we need the normal force. Okay. So I cannot draw this person, obviously. What I can do is identify my right angle. And then we know this is 60 degrees. We'll call this one not theta, but alpha. I could have picked any other Greek letter. Just it is very common for us to use alpha or phi. Some people say phi. I don't even know what's the right one, phi or phi. So I just stick with alpha. That way, if one of those is, of course, I don't know if one of those would be mispronounced, but I don't want to mispronounce more stuff because I already mispronounced a lot of stuff. Okay? So alpha is 60 degrees. So then I will label it over here. Alpha is 60 degrees. And don't worry, I'll tell you what theta is right now. And let's draw the person. Let's use some other color. Purple is fine. And I'm going to assume this person is a rectangular prism. Yes. As I said on the other video, for unit number 5, we're going to say things like assume a cow or a penguin or whatever is a cylinder or stuff like that, or a sphere, right? It makes the math easier. Okay. Now you know what? I'm going to redraw this one. I'm not doing any justice to the person, so one last try. That's not bad. That's not bad. Okay. And it is always good for us to state the direction of motion. Let me fix this a little bit. We state the direction of motion. So this victim is being lowered, right? So down the incline. We'll put green. This is the direction of motion. It's parallel to the plane. It's in the opposite direction, like that, right? That's how this person's moving in the sled. So there you go. And then I will label this as motion. That way I can know this represents the motion. There you go. And then the force that is present always, because we are on planet Earth, is the force of gravity. In this case is the weight, right? The weight, that's this W. Don't get it confused with watts or work. That's why I don't label it as W. I like to label it as mg. So I know it's the weight of the person. And it's going down, straight down, right? Because we said if by some reason, maybe quantum mechanics, we don't know, this would disappear, right? If there was no hill, then this person would fall down like this, straight down. Okay. And we have this force, the tension, right? Because of the rope, and it's pointing up the incline. And they're lowering the person, but this rope is holding, right? So it's fighting against gravity, right? Because if the rope snapped, this person would just slide down. So it's away from the center of mass. So this would be, maybe, let's see. Yeah, this is decent. This would be not just the, well, they have two arrows, right? I don't like doing two arrows. I just like to do one arrow and then identify the force or the forces that are acting along this direction. In this case, it would be tension and would be friction as well. Why friction? Well, friction is always against the motion, right? It opposes motion. If the motion is down the incline, then friction is up the incline. This is tension plus friction, and we have one more, right? We know that if there's a surface and we have gravity, we're going to have a normal force. Don't forget, I'm going to say this again. When we say normal force, not natural, because for some reason you guys like to say natural force, what that means is a force which is perpendicular to the surface. What is the surface? Well, this is an inclined plane or this triangle. It would be the actual hill, right? So this is the surface. So to draw the vector for the normal force, I'm going to have to do a vector which is perpendicular, right? So there you go. Now just move it. There you go. And that is the normal force, which has a weird N as a symbol. Right? Do this weird N so you don't get it confused with newtons. There you go. Now our free body diagram is complete. However, we know that the normal force is a reaction force. If you recall Newton's third law of motion, for every action force, there's an equal and opposite in direction. Equal and opposite in direction reaction force. Okay, so the normal force is a reaction force. It's equal and opposite to a force pointing this way, right? Because based on Newton's third law of motion, we need a force equal and opposite to the normal, which was the action force, right? Because the normal is the reaction. So that means there's a force acting like this, kind of. There you go. Now, although the magnitudes might not be equal, so let's pretend they are, okay? And so what is this force? Well, we always want to have our coordinate system so that it matches the motion. So the motion would be down the incline, right? So that has to be either x or y, because normally our x is horizontal and the y is vertical. So I'm just going to copy this one from the previous video, so I don't have to do it again, right? We'll do a few changes as needed for this one. So if this is a coordinate plane, right, you can probably tilt it a little bit because our axes have to match. So this one has to be parallel. There you go. So this is our x, and then the y has to be perpendicular to x. There you go. And that's our y. Notice how the motion is down the incline, right? And we'll make this one positive x. Oh, come on. There you go. Because the motion is down the incline. So this is the component of gravity, which is perpendicular to the surface, or I call it mgy, the y component of gravity, right? Because this is the y-axis, so this matches the y-axis. So we'll say this is mgy. And then we're going to have mgx, right? Because if the rope would snap, right? If it snapped, then this victim would just slide down the incline because of the force of gravity. So this is, there you go. Let's make sure it's, there you go. That's not almost perfect, right? So this is the component of gravity along the x. So mgx. Again, we want to tilt our coordinate system, not plane, but system, so that it matches the motion, right? It's sliding at an angle, right, based on this slope. So we want to have this coordinate plane so the math is easier. Okay? So now we have all three forces with the components of gravity. And now, as I said in the other video, we should, if we have a free body diagram, we should sum the forces. So let's do that. Let's start with the y-axis. So the summation of forces along the y-axis. Now to know which one's negative, this one, we've just been using normal as positive, and this one is negative. So the normal minus mgy. Now, what is this equal to? Well, are they jumping? Is this person jumping? No, it's a victim, so they're probably hurting. So they're not jumping, meaning they're not moving like that, right? So that means, yeah, so like this, that's what I meant, right? They're not moving like that. So it's equal to 0. There's no acceleration along the y direction. And the only way these two can be, when subtracted, can be equal to 0 is if they are equal to each other, right? The only way two numbers, when subtracted, can be equal to 0 is if they are equal to each other. There you go. So now we'll sum the forces along the x direction. I said x direction. And this is the x direction. Okay, now some students ask me, so what do we do about this one? Well, this one is moving both along the x, right? It's moving sideways and down, so both directions. That's why we break it into components. So we have mgx, tension, and friction. So how do you know which one's positive? Well, we said that once we find the direction of motion, make that one positive. So this one would be positive, mgx, right? Because the motion is down the incline, and that matches mgx. So it would be, wait, I need a bit more space. I have more forces here. mgx plus, no, minus, right? Because this is in the opposite direction. Parentheses, tension plus friction. Before I tell you what this is equal to, I need to, well, I mean, I don't need to, right? But I want to simplify a little bit. Because this might confuse you a little. So before I tell you what this is equal to, I'm going to distribute this negative sign to these two. So that'll be summation of forces along the x is equal to mgx minus tension minus friction. Now, how do we know? Because some people say, well, there's gravity, so there might be an acceleration. However, I told you this was very important. It's at a constant speed. Constant speed, cruise control, that is constant velocity. If you don't have a change in velocity, we don't have acceleration. If we don't have acceleration, we don't have a force, because force is equal to mass times acceleration. So this is equal to 0. There you go. We have the summation of forces. So now let's try to find the work done by friction. Okay. But to find the work done by friction, we need the normal force, and we don't know what the normal force is. However, we know that the normal force is equal to the y component of gravity, mgy. We don't have mgy explicitly, but we can find it. I'm sure you saw how with trigonometry, right? Now I take these forces. I want to copy this one over here. Let's do it here. It's fine. No. I want the space for the equation. So let's make this one bigger so we can see a little bit better. Yeah, here's fine. A bit more. I'm going to clean it up. I don't need alpha, I don't need this, and I don't need this. I'm going to move these forces, well, at least make them smaller. Okay, so as you know, we can move vectors, so I'm going to move this vector over here to get my right triangle. This is mgx down the incline. This is mgy perpendicular to the incline, and this is mg, the weight. Okay, I'm sure you guys saw where the 90-degree angle is, this one. Now this triangle is a reflection of this one. So theta will not theta, alpha is not this one, right? Because this one's like the top one, you could say. This is alpha over here. Then we can use trig, right? So let's start with the mgy, right? Because normally we start with the sine, but let's start with mgy. Mgy is the adjacent side to alpha. So we have adjacent, we have the cosine. So we say cosine of alpha is equal to the adjacent side, which is mgy, divided by mg. We're trying to solve for mgy. I multiply mg to both sides, and now I have that mgy equals mg cosine alpha. Again, I'm sure you guys can guess what the what mgx is going to be, because now we use the sine of alpha is equal to the opposite, that is mgx, divided by the hypotenuse, that's mg. We solve for mgx. In the same way, we solve for mgy, and we have that mgx is equal to mg sine theta. Okay, you have those two. There you go. Now let's try to find the work done by friction, okay, by using this equation. Let's copy it. There you go. Now here's the problem again. Well, not again, but here's the problem, right? We don't know what theta is. To know what theta is, so again, 60 degrees is not theta, okay? Theta is something else. Theta belongs to the force, which we're looking at, in this case, friction. So we have to know the relationship between the force of friction and the direction of motion by means of theta. What I'm trying to say is, what is the angle between the arrow representing direction of motion and the vector force of friction? So to know, I can move my vector for friction, for motion, and then I see, okay, so this is the direction of friction, right, up the incline. Direction of motion is down the incline. So now I have to find how much of a circle, how many degrees can I move, or how much of a circle can I draw if I go from the end of the direction of motion, this one, to the tip of the friction force vector. I'm sure you guys can see. I'm going to try to draw it. It's going to be very bad, but it is half a circle. And half a circle is 180 degrees. Again, we have to find the direction of motion, then compare it to the direction of the friction force. They have opposite directions. Okay, opposite directions. So now I can say the force of friction, the force of friction, theta is equal to 180 degrees, half a circle. And the cosine of 180 is -1. If you don't believe me, go to Desmos and get the cosine of 180, okay? And whenever you have an inclined plane, at least for our class, we use an inclined plane usually to maximize the work. And we said that we would maximize the work when the angle theta was 0. In this case, it's 180 because they have opposite directions. Normally, we had a force acting along the same direction as the motion, and this one is opposite. So then we can say work done by friction equals force of friction times distance times the cosine of 180 degrees. That'll be -1. Work done by friction equals Fd times -1, and that is simply -Fd. Okay, so now we do have the distance. Let's find the friction force, right? The equation for friction, I don't think I wrote it down, so I'm going to write it down over here. The equation for force, oh no, I did, here. Coefficient of friction times the normal force. So let's keep going. The work done by friction is equal to the coefficient of friction times the normal force times distance d. Okay, I do have the coefficient of friction, and we do have the distance. We need the normal force. We didn't have the normal force. However, we found that the normal force is mgy is equal to mgy, and we saw that mgy was equal to mg cosine alpha. I do have the mass, I do have acceleration due to gravity, and I do have the angle alpha, which is 60 degrees. So now I can say work done by friction equals negative mu times mg cosine alpha times the distance. Okay? And I'm just going to do a little arrow showing that the friction force is equal to mu mg cosine alpha. And I got it from the coefficient of friction times the normal. The normal is mgy, which is mg cosine alpha here. Okay? Now I'm going to get the letters with the letters. Mu is a Greek letter, so it does qualify. It does qualify. It sounded like I said it is qualified. So mu mgd times the cosine of alpha. And that is it, because we have all of the variables. We have the coefficient of friction, mass, acceleration due to gravity, distance, and the angle alpha. Don't forget, make sure your calculator is on degree mode, not radians, okay? And once you substitute, once you plug it in, you're going to find the answer. And I'm going to leave it like that.